Hey guys,
Hello!
Addie's got some more transistor stuff for us this week.
Transistor circuit of the week number 2. So this week, this was chosen by Adam Fabio, AJ Fabio, theengineer.com.
Who, knowing Adam didn't actually build the circuit.
Well, either way, he chose Forrest Mims's dual LED flasher, and that's what we have here up on the screen. So I thought I'd just go through it. It's actually a really easy flip-flop circuit. Makes two lights go back and forth. But this particular circuit uses PNP transistors, and PNP transistors are slightly different from NPN in that the basic function is that this base has to be lower than like the voltage at the base has to be lower than the voltage at the emitter for the emitter to conduct electricity from E to C. And charge from E, this emitter, or from the power source, kind of puts out a trickle of current through B, and that trickle of current is amplified through C. Does that make sense at all? So whereas NPN's B would act like a gate, allowing, switching on or off the transistor, in this case it's the relation of B, of the base, to the emitter. So as long as the base voltage is lower than the emitter voltage, then power or current will go from E to C, from the emitter to the collector. So that being said, what happens is this circuit, when it first charges up, because the voltage at B is lower than the power source, these transistors will be on. And they'll be on, and so they'll conduct electricity from E to C. And as they do that, the current that goes through C will charge up these capacitors here. And if you know anything about capacitors, you know that with AC voltages, it allows the AC voltage through. So assuming there's some sort of AC voltage here, the AC will go to the base of the opposite transistor, right? So we've got electricity, or we've got charge coming through here, charging up the capacitor, but also AC style, bringing up the voltage here at the base, right? And again, as this base voltage increases up to the point where it's greater than the emitter voltage, once that happens, then the transistor turns off, right? So when it turns off, then the capacitors will end up discharging, right, through the resistor, this current limiting resistor, through the LED, which will keep the LED lit, and then eventually go out to ground. And this circuit kind of works on the fact that these capacitors will charge up maybe at slightly different rates because of their different properties, or that these transistors will conduct slightly differently because of their own intrinsic properties, like manufacturing or what have you. So let's go through that one more time. So we have the voltage source. When we turn it on, the base voltage of both of these transistors will be probably near zero, which means that this transistor is turned on. When this transistor is turned on, current will go from the emitter to the collector. And as it does that, so the LEDs will obviously be lit since there's current going through the through this segment. But as the current goes down here, it also helps to charge these capacitors. These capacitors allow AC voltage through, which will cause the opposite base of the transistors to go up to a higher voltage, high enough to where it overrides the emitter voltage, and once VB is greater than VE, then this transistor will turn off. When this turns off, the capacitor will discharge through the LED down to ground, and then you kind of start it up again. So I'll show you guys a simulation that we did to demonstrate this a little better. What we have here is the circuit in our little simulator again, and I'll reset it for you guys, but keep an eye on these two LEDs here. So you see that both of them light up immediately. Because these transistors are both on, they're both allowing current to go through, and right now they're pretty much charging these capacitors, which I have at 5 microfarads, just to show you guys more easily what it looks like. And once one of these sides gets to the point where it turns off, then you'll see no current goes through. But as soon as it finishes relaxing, and as soon as this voltage at the base gets lower than the emitter, then you see that the transistor allows current to go from the emitter to the collector. And just to show you guys where the emitter and collector are. So this side is currently, the transistor is on, now off. On, and now off. So again, whenever this is allowing charge to go through, or whenever one side is allowing charge to go through, the other side is resting, and its capacitor is discharging, and the voltage from the base side of the transistor is pretty much going, you know, decreasing through ground. Does that make sense, Whisker?
Mm-hmm.
Yeah, kind of cool, right? So depending on how you change these capacitor values, these LEDs might be on for longer periods of time, or shorter periods of time. You might see more fade. I think too small, if the capacitors are too small, then you'll end up seeing, you know, way too much flicker. And now I actually have a real version of it to show. Okay, so I won't go through the entire steps, but just to show you that we have 2 LEDs, we have the 2 transistors, and just an FYI, total noob mistake on my part. So the drawing that Forrest Mims has makes it look like the transistor is symmetrical, like backwards almost. It is in fact not. So these transistors shouldn't be backwards from each other. If you have questions about my noobness, feel free to ask. Anyway, just wanted to show you this is on a parallax demo board. I was too lazy to break out a normal breadboard, so this ended up having to work. And voila! We have a simple dual LED flasher, and it is pretty much all analog, right? There's no
Totally.
yeah, there's no microcontroller controlling it or anything like that, and you can pretty much control how fast these go based, again, on the
Capacitor.
Exactly. Yep.
Cool.
So there you go. Transistor
Alright.
circuit of the week 2.
Alright. Well, that's it for us. We'll see you guys next week.
Bye.
We post videos all the time, so don't forget to subscribe and follow us on Twitter at TYMKRS.